Okay, it's my pleasure to welcome Maria Chudnovsky. She will talk about induced graphs and tree decompositions.
All right, should I start? Just a minute. I can't see myself, and I'd like to see myself. Just give me 1 second. I said I was ready, and I was wrong. Okay, now I'm ready. No, I'm not ready. I still can't see myself for some reason. I'm really sorry about that. I don't know what happened. Okay, this is good. All right. So, Dmitry, is it possible that you're spotlighting yourself? Because I keep getting your picture instead of mine, no matter how much I'm talking. No? Okay. Okay. Possibly it's set up to spotlight the host. All right. Anyway, I think I figured it out. All right. So anyway, thank you for having me. Sorry for the technical difficulty. And so this is my pandemic talk. I'm basically going to be talking about things I've been doing since COVID-19 hit. As somebody here said, there's a lot of time to do math now, so it's a couple of theorems. All right, so I'm a graph theorist. I think about graphs. Graphs have vertices and edges. And for most of my mathematical life, I've been thinking about families of graphs defined by forbidden induced subgraphs. So what does it mean? You fix some graph, and now you're interested in those graphs from which you cannot get the graph that you fixed by deleting vertices. Right? Taking induced subgraphs just means deleting vertices. And then you want to know what can you say about a family that's defined in this way by forbidding configurations and deleting vertices. I'm sorry?
When you delete a vertex, you delete all the edges coming into the vertex?
Yes, yes. Okay. So I'm about to define this more rigorously. So here we go. H is an induced subgraph of G, is the vertex set of H, is contained in the vertex set of G. And then you keep edges if, first of all, you kept both their ends, and secondly, you keep every edge that was there, right? You're obviously not allowed to add edges, but you're also not allowed to delete edges if you kept both ends of this edge. So this is a little different from possibly the most popular notion of graph containment, that of being a subgraph. And that's when you're allowed to delete vertices and you're allowed to delete edges. But here you're constrained on how you can get rid of edges. Okay, so here's an example. This is G. This is an induced subgraph of G, because to get this from that, you can delete this vertex, and then you delete all the edges instant with it. This is not an induced subgraph of that, because to get this from that, you need to delete this edge and this edge, but you're not allowed to just remove edges, right? You can get rid of edges if you're not touching their ends. And I'm going to say H is contained in G if H is isomorphic to an induced subgraph of G. So everything is up to isomorphism. I'm not going to worry, is it the same vertices or different vertices? So I'll only say this once. H is contained in G, or sometimes I'll just say H is an induced subgraph of G, but what I mean by that is H is isomorphic to an induced subgraph of G. And a family of graphs is said to be hereditary if it's closed under taking induced subgraphs. Now I'm a little curious how the field of induced subgraphs got control of the word hereditary. Hereditary is such a convenient word for any lower ideal, but somehow in graph theory, hereditary is used for induced subgraphs, at least as far as I know. Okay, so then I can rephrase this statement as saying I'm interested in the structure of hereditary graph families. Okay, so now probably the most well-known, one of the most well-known hereditary graph families is a family of perfect graphs. So a graph is perfect if and only if for every induced subgraph, the chromatic number and the clique number are the same. And just to remind you, the chromatic number, so chi of h is the chromatic number, and that means you want to color the vertices so that adjacent vertices get different colors, and you want to do it with as few colors as possible. So the smallest number of colors that you need is called the chromatic number. And then the clique number is the maximum number of pairwise adjacent vertices. So obviously the chromatic number is always at least the clique number. And it turns out to be an interesting question, when are they the same? And it turns out to be an even more interesting question, when are they the same but close under induced subgraphs? When are they the same for every induced subgraph? So this notion was defined by Claude Berge in 1961, and it has all kinds of interesting aspects to it. It generalizes all kinds of theorems that were known at that time. It has connections in communication theory, but I'm not going to tell you any of that. What I will tell you is that there is a forbidden induced subgraph characterization for the family of perfect graphs called the strong perfect graph theorem. And that was conjectured by Berge when he defined perfect graphs, and it took about 40 years to prove. And finally, with Neil Robertson, Paul Seymour, and Robin Thomas, we were able to prove it in 2003. So a graph is perfect if and only if it does not have odd cycles as induced subgraphs and complements of odd cycles as induced subgraphs. So let me just say something about this. So what's an odd cycle? It's probably, you can imagine what it is. It's a graph with an odd number of vertices, which you put in cyclic order. You make consecutive ones adjacent. You don't make you make non-consecutive ones non-adjacent. And you observe that in an odd cycle, the clique number is 2 and the chromatic number is not 2, because if you go 1, 2, 1, 1, 2, 1, 2, you eventually get stuck. So in fact, the chromatic number is 3. And this is C5, but the same argument works for C2k plus 1 if k is at least 2. Doesn't work for a triangle. So what does that tell me? That tells me that if a graph is perfect, then it cannot have an odd cycle as an induced subgraph, because for perfect graphs, the clique number and the chromatic number needs to be the same for all induced subgraphs.
Question.
Then, I'm sorry?
Could you say this a logical statement more slowly? I can't understand. I know all the concepts, but just
Sure.
the logical statement.
So
Something perfect if and only if for every cycle of length 2k plus 1.
so first of all,
I don't know. I mean, what's the logic of that statement? What's the sentence of that logic? What's that English sentence?
the one I just said?
For the theorem, yeah. Just say the logic. I can't understand it.
Oh, this one? Okay.
Yes, yes,
G is perfect if and only if
yes.
any C2k plus 1 is not an induced subgraph. So if and only if
What's
no induced
what's the
subgraph of
C2k
G.
plus 1?
What?
What is the C2k plus 1?
C2k plus 1 is this picture I drew here. It's the odd cycle.
Okay.
So
So what does it mean? What does that line mean? C2k plus 1 not equal less.
is not an induced subgraph of G. So over here I said,
Oh,
we'll write H is an induced subgraph of G.
okay.
H is
If and
contained
only
in G.
if.
If H is an induced subgraph of G. And then here it says a graph is perfect if and only if C2k plus 1 is not an induced subgraph of G for every k at least 2, and the same for something called the complement of C2k plus 1. And what I was explaining
I
here,
don't understand it. I don't understand it.
can you give me a hint as to what you don't
What's this little
understand?
symbol here? You wrote the same thing down twice.
No, because here there's a C, which means C2k plus 1 complement.
Ah,
Better?
see? So, okay, so now what's the whole sentence again? Now I see the notation.
Okay,
Say the
now the
sentence.
whole sentence is,
Just say the sentence.
a graph is perfect if and only if no induced subgraph of it is C2k plus 1 or C2k plus 1 complement, where k is at least 2.
Oh, no subgraph is either a cycle or the complement of a cycle of odd
That's
length.
That's right.
Okay,
No induced subgraph.
no induced subgraph. Thank you.
Okay, and then odd length at least 5. k at least 2. All right.
Yeah.
Okay. And what I was saying on the board is that so one direction, at least if we think about cycles for a minute, one direction is clear because if you look at an odd cycle, the clique number and the chromatic number are not the same. And so it cannot be an induced subgraph of a perfect graph, because for perfect graphs, the clique number and the chromatic number are the same. And you can do the same thing for complements. Taking complements just means changing all adjacencies. You start with a graph, and then if two vertices were adjacent, you make them non-adjacent. If two vertices are non-adjacent, you make them adjacent. So you can see that an odd cycle cannot be an induced subgraph of a perfect graph. It was a little bit more effort. You can see that the complement of an odd cycle cannot be an induced subgraph of a perfect graph. And the hard part of this theorem is the if and only if part, right? So to show that if you don't contain any of these as induced subgraphs and you don't contain any of those as induced subgraphs, then your graph is perfect. That's how. All right. And I just want to say one other thing.
I have one more question.
Sure.
What does the complement mean?
The complement means you change all the adjacencies. You start with a graph, and now if two vertices were adjacent, you make them non-adjacent. If two vertices were non-adjacent, you make them adjacent. And the new graph that you got is called the complement.
Yeah, but what does it mean to apply it to C2K plus 1?
So let me show you an example.
Well, life example.
So here's C5, and it has vertices 1, 2, 3, 4, 5. Now I'm going to draw the complement. Vertices are 1, 2, 3, 4, 5, and then 1 used to be adjacent to 2 and 5, so now it's going to be non-adjacent to 2 and 5, but it will be adjacent to 3 and 4. 2 used to be adjacent to 1 and 3, so now it will be adjacent to 4 and 5. 3 used to be adjacent to 2 and 4, so now it will be adjacent to 1 and 5. And you got this graph, and it actually happens to be isomorphic to the graph you started with, right? Another C5, just go around like this. But if you start with a longer cycle, then the complement will not be isomorphic to the graph you started with.
Thank you.
Okay. Okay. So, and as I said, perfect graphs, they were defined in this way, but they have connections to all kinds of other concepts. And one thing that's that I would like to point out is that for perfect graphs, you can solve several problems that are NP-complete for general graphs. On perfect graphs, you can solve them in polynomial time. So one such problem is computing the clique number, right? It's NP-complete in general, but if the input is perfect, you can do it in polynomial time. Then,
polynomial in what? Polynomial number of vertices?
Yes.
Okay.
Which is the same as polynomial number of edges, because edges are polynomial, they're n-squared edges.
Right.
So you can also compute what's called the stability number. So the stability number, a stable set is a set of pairwise non-adjacent vertices, and then the stability number is the size of the largest stable set. But from here, you can see that a graph is perfect if and only if its complement is perfect, right? Because this statement is invariant under taking complements. So that means if you can compute the clique number in perfect graphs, you can compute the stability number in perfect graphs, because stability number is just clique number in the complement. Right?
What's the degree of the polynomial they have?
I don't know. I can't tell you, sorry. But I will say something about this algorithm. And another thing you can do in polynomial time is color the graph. One thing I want to say about this problem, so you can do it, there are algorithms, but they all use something called the Ellipse Method. So you take your problem of computing let's say the clique number, and you write it down as a combinatorial optimization problem, as a semi-definite program. And then you hit it with tools from combinatorial optimization, which I cannot and will not talk about. And then an answer comes out. But what's open, and I think is very interesting, is solve this problem without going through continuous notions of combinatorial optimization. Solve this problem just using what's called the combinatorial algorithm. Just say it in terms of the graph, right? It's a problem about graphs. So give an algorithm which you can say in terms of the graph rather than go and look at some polytope and dive in and out and find an optimum of some problem. So that's open, and it's one of my favorite problems. I'm working on it almost at all times. And I'll maybe say something about it later. All right, so moving on. So I showed you hereditary family, which was very nice. It's well known for a reason. It's well known because it's a nice family. And then one asks, are all hereditary families nice? Is there something that's good about all hereditary families? And it turns out that the answer is no for almost any concept of nice that you can come up with. So let me tell you two concepts for which the answer is no. One is, so for perfect graphs, the clique number and the chromatic number were the same. What if I ask him, what if I make a much less ambitious requirement, and I say I want the chromatic number to be bounded as a function of the clique number? Is it true that for every hereditary family there is a function that does that? It's not true for all graphs, but maybe it's true for a hereditary every hereditary family. And the answer to this question is no, because even for triangle-free graphs, so you cannot find such a function. There are graphs with no triangle and with arbitrarily large chromatic number. Now, graphs with no triangle, so their clique number is 2, and their chromatic number is arbitrarily large, so there's no such thing, right? Another question you can ask is, maybe you can always, solve problems in polynomial time. Maybe the fact that it works for perfect graphs is an instance of a much more general fact. But in fact, it's not. For example, computing omega is NP complete even for graphs with no stable set of size 3. Right? A graph with no 3 pairwise non-adjacent vertices, it's already hard to compute omega. There's one lovely conjecture that it's a conjecture, but at least it's not known to be false, and it does say something nice about all families of all hereditary families. It's called the Erdogan conjecture. It's from about 1989, and what it says is the following: for every h, there's an epsilon, so that if I look at a graph that does not contain h as an induced subgraph, then in this graph, either there is a surprisingly large clique or there is a surprisingly large stable set. So what surprisingly means the number of vertices of G to the power epsilon, right? So asymptotically, the clique number or the clique or the stable set size is polynomial in the number of vertices. Now, just so I said surprising. What does it mean surprising? Well, if you look at a random graph, which doesn't have forbidden induced subgraphs, which contains all induced subgraphs, then you expect alpha and omega to behave as log the number of vertices. So somehow what this conjecture tells you is that the local property of excluding an induced subgraph has a global effect on the whole graph, because suddenly the asymptotic behavior of these parameters changes from being logarithmic in the number of vertices to being the number of vertices to a power. And just for notation, alpha of G is the maximum number of pairwise non-adjacent vertices, the biggest size of a stable set. Yes?
Sorry, what if I just take epsilon h to be 0?
Right, so it should say bigger than 0. It should say bigger than 0 and less than 1.
Thanks.
Sure.
Thanks.
Anything else? Okay. Yeah, no, for 0, it's no. All right. So, so then let me switch gears and let me ask, which hereditary families have nice properties? So it's a big field of study in graph theory. Which hereditary families have this property? There's been a lot of work done there recently, but I will not talk about that much. What I want to focus is two aspects of being nice. One is structure. So for which hereditary families can I say something interesting about the structure of graphs in the family? can I describe the graph somehow more explicitly than they don't contain a certain induced subgraph. And then another topic I want to think about is efficient algorithms. All right, so let me start with that. All right, so I said a nice structure, more explicit than just forbidding an induced subgraph. So it's, it's a very open-ended question. But let me tell you a concept from structural graph theory that somehow everybody agrees is a good way to describe structure of graphs. So it's called a tree decomposition. And I'll tell you the definition, but I mean, this slide is for a niche group of people who probably have seen this before but forgot. Because if you haven't seen this before, it's too fast. And if you didn't forget, then it's unnecessary. But I'll say something. I'll give you some high-level idea of what I want to say. Okay. So I have a graph G, and I want to construct something called the tree decomposition of G. So the tree decomposition of G has a tree, and now you try to represent G by this tree. What do I mean by that? So first of all, I'm going to every vertex of this tree, so to every node of this tree, I'm going to assign a subset of vertices of G, right? So it's not disjoint subsets or anything like that. Just I'm saying every vertex of the tree, in it sits a bag of vertices of G, right? So it's this like for every V in VT, there's a bag of vertices of G. And there are two rules. One rule is every edge of G needs to be caught by some vertex of T. So for every edge of G, there's a vertex of T, so that both ends of the edge are in the bag that we mapped to that vertex. And the second rule is for every vertex of G, its support in T is connected, right? So if you look at vertices of T in which X appears, that needs to be a subtree of T. And this is completely non-intuitive. In 2 slides, I'll give you some intuition for it. I just want to quickly show you an example to make it a little bit less unclear. So here's a graph G. Here is its tree decomposition. So here the graph G itself is a tree. I'm going to construct a tree decomposition using the same tree. So the pink thing is a tree T. The blue thing is a graph G. And what I want to, so now I need to assign these bags. Well, so they're written down here. Let me not explain to you how I got there, but you can check like 1, 2 is an edge. It's mapped to, both vertices are mapped to this node. 4, 5 is an edge, both 4 and 5 are mapped to this node. You can check it's true for every edge. And then let's see, what's the support of 1? So 1 appears only here. That's a tree. That's good. What's the support of 3? 3 appears here and here and there. So that's a tree. That's good. And then this is another example doing the same thing for a cycle. And one thing you should notice is that here I used bags of size 2, and here I'm using bags of size 3. And I'll come back to that in a minute. OK, so that's some representation of a graph using a tree. And then I want to quantify how complicated this representation is. And my quantification is by how big the bags are. How many vertices did I throw into each vertex of T? That is a very simple tree decomposition. Take a 1 vertex tree and put all of G on that vertex. Well, that's a tree decomposition, right? Everything is satisfied. Every edge is in a bag, and for every vertex, its support is a tree. But somehow, this is probably not what I had in mind. So that's too complicated. So I want to talk about width, which is how big the bag is, and you subtract 1 for reasons that will soon become clear. And then the tree width of G is the minimum width of a tree decomposition. So I don't mind making T huge. Any tree for me is good enough. But what I would like to do is make the bags small. Say I'm putting not too many vertices on every vertex. And the thought is that if G has small tree widths, then it's somehow close to a tree. And if G has huge tree widths, then G is very far from being a tree. So here, for example, I was able to represent a tree with bags of size 2. This is a cycle. I use bags of size 3. And in fact, it's not hard to convince yourselves that you cannot use bags of size 2. So to use bags of, to have a tree representation, tree decomposition with bags of size 2, you need to be a tree. So tree width of the tree is 1. That's why you subtract 1 here, so that it comes out the tree width of the tree is 1. All right, so anyway, so all we want to say, all we want to get out of this is that it's some representation of the graph by a tree in such a way that every edge of the graph is caught in some node of the tree. Now, why is it good for you? Well, it's turns out to be, if you have a bounded tree width, a bounded width decomposition of a graph, then it turns out to be very useful for algorithms using a method called dynamic programming. And I'll show you something from that, and then I think you'll understand what the point of tree decompositions is, at least in what I'm trying to describe. So, all right, so let's say I'm solving an optimization problem. I'm trying to find alpha of G. And just to remind you, alpha is the biggest size of a set of vertices with no edges inside. And suppose I have a tree decomposition of my graph where all bags are smooth. So I'm now drawing the tree already with bags in it. This is, on one hand, this is a tree, but on the other hand, this little circles represent the bags that correspond to vertices of this tree. Okay, so I'm going to solve my problem from the leaves of the tree. So certainly I can find the best stable set inside this bag. Why? Because bags are bounded size. So I can just go through all subsets and see what the biggest stable set is. And I can do it in every leaf. And now I'm going to try and do it for bigger and bigger subtrees. So let's say I've done it for this subtree and this subtree, right? So I can find the biggest stable set that's mapped to this subtree and the best stable set that's mapped to this subtree. And now I claim I can get the biggest stable set that's mapped to this subtree. So what I'm going to do, my first naive attempt will be take the union of the best guy here with the best guy there. Well, what's the problem is taking the union of two stable sets that maybe there are edges between them. But this is a tree decomposition. And what that implies, and that's the only property I care about at the moment, is that every edge between this subtree and that subtree is actually caught by this bag. So if I take a stable set here and a stable set there, every conflict that I might get between them is captured in this bag. Well, then I'm going to do the following. For every stable subset of this, of which there are only constantly many, because this is bounded size, I'm going to find its best extension in this direction and its best extension in that direction and take the union. And now I'm guaranteed that there's no conflict because all conflicts will be captured here, and I made sure the intersection with this does not pose a conflict. And so that's how it works, and there are all kinds of problems you can solve this way. There are beautiful theorem and logic that tell you what kind of problems you can solve this way. But what I want to say is I didn't actually use that the tree width was bounded. What did I use? I just used that in order to avoid conflicts inside this bag, I didn't need to check too many things. I just needed to look at a bounded number of subsets of this bag, right? And in fact, polynomial would also work. So if I somehow could find a tree decomposition, right? So now I have an optimization problem in mind. And suppose I could get a tree decomposition which is not of bounded width, but which has the property that every optimal solution meets every bag in not too many vertices, or maybe even in a lot of vertices, but in not too many ways. I could do exactly the same thing, because all I needed to do here is for every possible way that my optimal solution meets this bag, I needed to check something in smaller graphs. Okay, so that's what I want to focus on. How can you abstract bounded tree widths? So I want to think about properties of bounded tree widths I need for this to work, and then see if I can get decompositions that have these properties. Okay, so what can replace bounded tree widths? And as a structural graph theorist, what makes perfect sense to me, but turns out to be pretty much useless or often useless, is the following. I'm going to get the tree decomposition, meaning to every vertex of the tree, I assign a bag of vertices of G and all edges are caught and all that. But what I know is that every bag belongs to some simpler class of graphs than the graph I started with. So that seems like a very natural thing to do, right? You decompose the graph in some ordered manner using a tree, and what's, each piece of your decomposition is simpler than the graph you started with. You'd think that should be wonderful, but so far it's not wonderful. If I have time at the end, I'll show you one theorem that uses this idea, but somehow you don't get the world if you manage to do this. Here's what sounds less natural, but works better, at least for algorithms. And it's something I mentioned when I was working on the board. With an optimization problem in mind, find a tree decomposition where every bag meets a solution in a bounded number of vertices. So then, if I could somehow construct such a tree decomposition, I could do the thing I did back there. The problem is, it seems circular, right? I have an optimization problem in mind, but I want a tree decomposition that meets the optimal solution in certain ways. Well, if I knew so much about the optimal solution, probably I wouldn't need to solve the optimization problem. So let's make this a little more plausible. And that's an idea of Bushita and Todinka from the mid-1990s, or maybe the early 2000s. So what they said is, if you can build a list a list of subsets of your graph, so that let me start again. They were thinking about computing alpha. They were thinking about computing the stability number. So if I could build a list of subsets of the graph, so that every bag of a tree decomposition that has the property I want is in the list, right? It's not hard to see that there is a tree decomposition with the property you want. It's just hard to find it. So, but you make a huge list of sets and you include all kinds of sets in there, but in particular, you include all sets that would appear in this decomposition that interests you, if only you can find it. Then you can compute alpha just using this list. You don't need to construct the tree decomposition. You don't need to know which subsets you guessed right and they are in your tree. They would appear in your tree decomposition, and which subsets you guessed wrong and they're just completely unrelated. If only you could produce a list of subsets that include all the sets you're interested in, then you can compute alpha in time, polynomial number of vertices of the graph, and the size of the list. So that's, of course, a caveat, right? Because the first thing that comes to mind is produce the list of all subsets. Then certainly you would include every subset you're interested in, along with every other subset. Well, and then you could compute alpha, but unfortunately the time will be polynomial in 2 to the number of vertices, which is not what we call an efficient algorithm. So, okay, so then they started saying, for which graphs can I build this useful list and make it polynomial in the number of vertices? For which graph families can I build this useful list and make it polynomial in the number of vertices? And they had a nice characterization structure, simple characterization of subsets that you want. And then it was just a question of for which graph families the list is polynomial. So let me say something here. So for which families can you build a useful list which is polynomial in the size of the graph? And then the second question is, well, maybe I don't need to include all possible subsets that might appear in the decomposition of the kind I'm interested in. Maybe I can, constrain it a little bit more. Constrain it a little bit more. I don't need to look at all decompositions. I just need to look at, to ensure that at least for one of them I include all the subset, all the bags. So you can try and see, can you demand a little bit less and still be able to solve your optimization problem? All right. So, and I'll say something about both questions. So for the first question, right, for which families is just this list. And what I wrote here is what these useful subsets are, but I think I'm not going to spend time on saying exactly what the requirements are. Just I want to include every subset that might appear in a useful 3D composition like that. So they were asking for which families of hereditary families of graphs does this list have polynomial size, and they were especially interested in these particular families. So this is a family of graphs that don't contain long cycle, or so don't contain cycles of length at least 5 as induced subgraphs, and don't contain complements of cycles of length at least 5 as induced subgraphs, right? So it's a subclass of perfect graphs, because here I'm forbidding all cycles and there I was only forbidding odd cycles. And it's a nice family. It's actually a fairly rich family, even though everything in the world is forbidden. So they could prove that in that family, this useful list they came up with has polynomial size, and then they could compute alpha for this family of graphs. All right, so then let me move on to the second question. Can you list a little bit less? Can you say, I'm not going to list all subsets that might ever be useful, but I'm going to pare down a little bit. And turns out this is a fruitful direction. So in 2014, this group of authors was able to weaken the requirements on L, so to say, I don't need to include all subsets, I need to include some important subsets, so that they could solve this, so they could find stability number in P5 free graphs and graphs with no path of length 5. And then a couple of years later, this group was able to weaken the requirements even more, so that they could solve the stability number problem in P6 free graphs. And then it stopped. It seems hard for P7 free or general PT free. But then last year with my student Tara Abrishami and Marcin Filipchuk, Paweł Żarzewski, and Paul Seymour, we did something else. So instead of, it's still the same idea, you want to construct this family from which you can kind of dig out the right 3D composition. But instead of listing precisely the sets that you need, precisely the sets that will become the 3D composition, the bags of the 3D compositions, we proved that it's enough to construct containers for these bags. And what's containers? So I want much larger subsets so that each of my useful bags is contained in one of them, right? I can, instead of listing each bag separately, I can aggregate them in this bigger subsets and containers. And you can still solve the problem if you can produce polynomial many containers. And it makes sense, right? It's to produce many little subsets, maybe you need a lot, but to produce, just big subsets that contain them, you can do it much more easily. Again, you might think just take one big container, the whole vertex set. That certainly a container contains every subset. So you need some properties for these bag containers. We call them safe bag containers, but it turns out it's easier to produce aggregates of bags than just to produce the bags individually. And so we prove the theorem that says, so we define containers, we prove the theorem that says you don't need bags, containers are enough, aggregates of bags are enough. And then we're able to solve, so to prove that this list has polynomial size for this family of graphs, which the problem was open before. So this is a slightly technical way to describe this family. But for example, it contains all graphs with no cycles of length 5, so of length at least 5. So those guys 20 years ago did all graphs with no cycle of length at least 5 and no complement of a cycle of length 5. We now did no cycle, just no cycle of length at least 5. And it also generalizes this result. So we can, our family also contains all P5 free graphs. So anyway, so it generalized a whole bunch of stuff. And not only that, we can solve a much more general problem than Max Taylor said. We can solve the problem of what's the biggest induced subgraph of fixed 3 width. I give you k, I want to know what the biggest induced subgraph of 3 with k in your graph is. And you can do it using this algorithm. And if you just think about it for a second, finding a stable set is finding a biggest induced subgraph of 3 with 0. Okay. So, all right, so that's going back to this question. How can you replace, what can replace bounded trivids? What other things have the same algorithmic properties as bounded trivids decomposition, because most graphs don't have bounded trivids. Okay, and then, so far I talked about this question: for which families can you generate a useful list of subsets that would allow you to solve all kinds of sorry, that's not what I meant to say. So far I've been talking about this question, question 2. There's some notion of a useful list of sets. How can you change this notion so that you can produce this list of sets for larger families of graphs? Now let me go back here. Now I want to think about the original question of Boschid and Todinka. Which families of graphs have the original lists, the original useful list that they defined in 2001 of polynomial sets? And now there is very good news about this, because it's a very sort of complicated notion, this useful subsets, right? It's hard to think about them, useful for what? But turns out you can replace it by a much more concrete question and then think about that. So it turns out that the answer to the question about this esoteric useful subsets is yes, if your graph has polynomially many minimal separators. And what's a minimal separator? Well, that's something we understand. A minimal separator is a minimal subset of vertices that disconnects some pair of vertices in your graph. Right? I deleted the subset of vertices. Now there is no path from A to B. But before I deleted the subset of vertices, there was a path from A to B. Right? So this is the subset of vertices I deleted is minimal that disconnects A from B. Right? And that's what it says here. X is a minimal separator if there exist A and B, so that there's no path from A to B with X deleted. But if you delete any proper subset of X, then there is a path from X to B. Right? So it's from A to B. So it's a, I mean, you understand what connectivity is. It's a minimal subset that changes, deleting which changes connectivity. And it turns out that it's enough to think which graphs have polynomially many minimal separators. So that's, a much nicer question. And let me just, right, so that's a new question for which hereditary families of graphs is there a C so that there are only the number of vertices to the C minimal separators. And it turns out there are some obvious things you need to exclude. So you need to exclude two large cliques joined by disjoint paths. You can convince yourselves that this has many minimal separators. You need to exclude two vertices joined by many disjoint paths. You can convince yourself this has many minimal separators. This has exponentially many minimal separators. There's a nasty example here. So it does not contain two big cliques with many paths between them. It does not contain two vertices with many paths between them. But somehow it contains a little bit of each. So it contains this clique and that clique, and there's three paths between them. Then contains this vertex and that vertex, and there's three paths between them. And then it contains this clique and this vertex, and there's three disjoint paths between them. So you'll only get this like little problems just with three, but still you can convince yourself that this graph has polynomially many minimal separators. And so then, led by this, we said, let's exclude everything that makes this so nasty. Let's exclude, so no 3 prism, meaning no two cliques of size 3 with disjoint paths between them. No 3 theta, that means no configuration like this with 3 rungs. No configuration like this of height 3, no configuration like this of height 3. So then it would also get rid of this example. And then it turns out you have n to the 18 minimal separators. It's a little mysterious why it's n to the 18. We did not try to optimize 18. Right? The question always is it polynomial or is it not polynomial? I doubt that 18 is the right answer, but 18 is what you could prove. And this is joint work with my student Arabi Shami, my student Jamil Debek, Nicolas Tornion, Stefan Thomas, and Christina Bushkovich. And then using everything that Pushito Tudinka proved, you can find maximum induced subgraph of tree widths K in graphs that don't contain any of those substructures. So now this theorem, it's if and only if in the sense that if you remove any one requirement, it becomes false. But it's not if and only if in the sense that it's not true that every graph with a 3 prism has a lot of separators. So here's a much more natural conjecture. How do you make a graph with many separators? So take two connected graphs, two disjoint connected graphs, this one and that one. And now put a bunch of disjoint edges between them, right? A1, B1, A2, B2, up to AK, BK, make K big. Have the A's only attached in the left connected graph, have the B's only attached in the right connected graph. And certainly you made a graph with a lot of minimal separators, right? Because however you choose one of A1, B1, one of A2, B2, and so on, you're gonna get another, a new minimal separator. So the number of minimal separators is exponential in K. And it somehow makes sense, right? That's what you need to have many minimal separators. You need some structure where you have choices for what to delete. So we made a conjecture that a graph has polynomial minimal separators if and only if it doesn't contain a K creature, where K creature is a substructure like this. But turns out it's false. It's so about a few months ago, Gartland and Lochsteiner found a counterexample. So I don't know what the right answer is anymore. I mean, apparently there's something else that makes it hard to separate the graph, not just this kind of thing. All right. So let me, in the next 10 minutes, let me get back to just the classical question of bounded tree widths. Right. So far I worked very hard to replace tree widths with something fancier, but now let's go back to asking what graphs have bounded tree widths. And so I'm interested in hereditary graph classes, so I want to know what hereditary graph classes have bounded tree widths. This question is answered completely if instead of thinking about forbidding induced subgraphs, you forbid minors. This is, it's deep theorems and people know, they've been known for a while, but it's unknown for induced subgraphs. Okay, so if I want to know which families have bounded tree widths, the first thing I need to do is list some families that don't have bounded tree widths so that I can say those need to be excluded. So here are some graphs with huge tree widths. A large clique has huge tree widths. A large complete biped graph has huge tree widths. Here's another graph that has huge tree widths. So this is called a wall, right? I mean, it's just these graphs that I've drawn here. I'm not going to explain to you what it is, but it's this picture. And then you can subdivide edges and you still have large tree widths. And then you can take line graphs. So a line graph means you build a new graph where the vertices are the edges of the graph you started with, and two vertices are adjacent if the corresponding edges share an end. So it's kind of an intersection graph of the edges of this. And what it means, if you wanted to do it pictorially, you replace each of these vertices by a triangle. Okay, so if you take the line graph of a large wall, it has huge tree widths. If you take subdivision of a line graph of a large wall, that has huge tree widths. Okay, so these are some nice examples, but turns out there are a lot more. So here's a very sad theorem of Cintiari and Tornion. They prove that if you take a graph with no induced even cycles and no clique of size 4, and it's not hard to see, if you know what to look for, that this guy contains an induced even cycle, and the line graph of a wall contains an induced even cycle. And of course, KNN contains C4. So by forbidding induced even cycles, they forbade this abstraction, this abstraction, this abstraction, and they also forbade K4. So they forbid every abstraction I told you about so far. And they can produce graphs like that of arbitrarily large druids. So these nice abstractions I told you about are not enough. You can still get huge, huge druids even if you forbid all of them. But what they noticed is that in their construction, the degrees are huge. So they build a graph that doesn't contain any of those things and has huge druids, but their examples have huge degrees, have huge max degree. They have vertices of huge degree. So then they said, well, what if we bound the max degree? What if we only think about graphs where the maximum degree is bounded? Then maybe it's true. And so they made a conjecture that it's true if you just forbid those abstractions and bound the degree. They also made a weaker conjecture. What if you forbid all even cycles and bound the degree? Is it then true that the clique number, that the druid is bounded? And so this is still open, but the weaker version, when you forbid all even cycles, all induced even cycles, is now known. It's a theorem with Tara Abishami and Kristina Bushkovich. So for every even whole free graph with degree at most delta, the druid is bounded by a function of delta. Let's see. Let me maybe say something about the proof. So the way you generally prove, it's going to be very quick. The way you generally prove that the druid of a family is bounded, you construct a collection of separations, a collection of cut sets in the graph. And you want to arrange that these cut sets are what's called non-crossing. And roughly what that means is they don't interfere with each other. They kind of line up. You know, this cut set, it has side A and side B, and this cut set, it has side A and side B, and either his A is contained in his A or his B is contained in his B. They kind of line up. They don't chop up the graph in uncontrolled ways. And then it's a theorem that if you can construct, if you can get a family of non-crossing cut sets, which are not too big, then so the family can be big, but each cut set needs to be small. Then your graph has bounded druids. Now, when you work with induced subgraphs, there are a lot of natural cut sets, and in fact, when the degree is bounded, so there are a lot of natural cut sets of bounded size, because usually the cut sets you get are, you take a vertex and its neighbors, or maybe you take two vertices and its neighbors. So there's no shortage of cut sets of bounded size, but they cross. They don't line up nicely. They kind of conflict with each other. They can decide which side is left and which side is right. But it turns out that when the degree is bounded, you can partition them into a bounded number of collections, each of which is what's called laminar, each of which is non-crossing, each of which has that property that's known to give you bounded druids. Okay, so now instead of one family of cut sets, you work with 100 families of cut sets, or a bounded number of families of cut sets. And turns out a lot of the same things work, and you can still get bounded druids, even though you had to look, you had to go, instead of doing it in one step, you have to do it in some function of max degree steps. And as you can imagine, I'm hiding 30 pages of calculations under the rug, but this is a very high level idea of this proof. And I think, let me stop now. I was going to show you another theorem about getting bags with, getting druids where bags are simpler than the graph you started with, but I don't think it's worth doing in the remaining 2 minutes. So I'm going to stop here. Thank you very much.
Thank you. Any questions?
Everything was completely clear.
Probably, yes.
And so I have a question about general hereditary families of graphs. So a hereditary family means that every subgraph has the same property. So do all hereditary families arise by prohibiting as a collection of subgraphs.
A collection of induced subgraphs. So hereditary family
induced
means
subgraphs.
you forbid a collection of induced subgraphs.
Right. So this means I need to just define. So I take any collection of graphs that I choose, and I can define a hereditary family by saying that no induced subgraph is one of these.
Yes.
And in what generality do these questions work? So your examples are somehow nice families. You have cycles or odd cycles, and then you throw in another prohibited subgraph or something like that.
So you're asking when do you get something nice?
Yes.
So it's a good question. I mean, I think the first question you should be asking is what's nice? And so I don't have a good answer to that. I don't know what's nice. There are various properties that you can see they're false for certain graphs, and then you say, what if I forbid all of those graphs?
Mm-hmm.
And then can I get the property, right? Somehow the way you would think about it, you would think of abstractions to having a property, and then you would say, if I forbid those abstractions, can I get the property? You know, is it true that I get the property? Like, let me maybe give you one example that I like at the moment. So there's this question of for which graph families can you bound the clique number as a function of the chromatic, can you bound the chromatic number as a function of the clique number?
Mm-hmm.
And so you can prove that if you forbid one graph, then you have to forbid a forest. If you forbid anything with a cycle, then you're not going to get that.
Okay.
So then the conjecture is if you forbid a forest, then you can bound the chromatic number as a function of the clique number.
Mm-hmm.
So that's a 40-year-old conjecture. Now, that's if I forbid one graph. Now, if you look at the reason why for one graph it has to be a forest, what you discover is that you need to forbid infinitely many cycle lengths. Right? You can't have, so you need to have infinitely many forbidden cycle lengths.
Mm-hmm.
So then the question becomes, what cycle lengths do I need to forbid to have this property? Turns out if you forbid all odd cycles, you get it. If you forbid all even cycles, you get it. I think if you forbid all cycles, I forgot, there are all kinds of modularity results, possibly even R mod T, you get it. So then the conjecture is maybe if you forbid any dense family in the integers, you get it.
Right. But
there's not a kind of theory of forbidding what is nice. You first define a property and then you try to
So what if I consider hereditary families that are obtained by prohibiting a finite collection of subgraphs? So I take any finite collection of subgraphs and I consider all graphs that do not have one of this finite collection as an induced subgraph. Are there some clear, nice properties this would satisfy? Because your examples are infinite collections.
Right. So there's a conjecture that no matter what you forbid, there's a huge clique and a huge stable set, any one graph that you forbid.
Mm-hmm. Okay.
And on the other hand, you know, there are some graphs that you forbid and nothing good happens, like graphs with no triangle are somehow very complicated. We don't have a concise description of graphs with no triangle, except that they don't have triangles. So I think the answer is forbidding a finite family of graphs does not necessarily give a nice answer.
Thank you.
In fact, forbidding infinite families works better somehow. You get something more topological because it's a little hard to explain, but you can start thinking about connectivity and being able to get from here to there to get your graph. Now it's about, you know, being able to construct a path rather than are these two vertices adjacent or not.
Mm-hmm. Thanks.
Sure.
Maybe a naive question. Does it make sense to consider tree decompositions of infinite graphs? And does it tell us?
So it does, but I'm really not the right person to talk about it. But certainly people think about it. Just, I don't know anything about it.
Okay. Okay, then thank you again. Yeah, and
Thank you very much for inviting me. I hope we can do it in person soon.